For centuries, physics was neatly divided into two distinct, comfortable domains. The mechanics of solid particles were governed by Newton, and the behavior of continuous waves was governed by Maxwell. Classical physics assumed that energy could take any continuous value. But at the turn of the 20th century, technological advances allowed physicists to probe the atomic scale, revealing phenomena that classical theory completely failed to explain. Welcome to quantum physics. In this unit, you discover a radical paradigm shift. You learn that energy is not continuous, but transferred in discrete, indivisible pockets called quanta. We bridge your prior understanding of waves and mechanics into the fundamental probabilistic rules that govern the universe at its smallest scales. Our first topic asks a profound question. Is light a continuous wave or a stream of discrete particles? You learn that electromagnetic radiation, traditionally modeled as a continuous wave, actually interacts as a stream of particles called photons. You master the fundamental photon energy equation, E equals hf, where h is the Planck constant. You also become completely fluent in converting these tiny atomic energies between joules and the standard quantum unit, the electron volt. This conversion is a critical skill for your exams.
Next, we tackle the photoelectric effect, the exact phenomenon that earned Albert Einstein his Nobel Prize and dismantled classical wave theory. You explain exactly why classical wave theory cannot account for the instantaneous emission of electrons from metals or the existence of a threshold frequency. Instead, the effect relies on a strict one photon to one electron interaction. You analyze the signature exam graph of maximum kinetic energy against frequency, extracting the Planck constant from the gradient, the threshold frequency from the x-intercept, and the metal's work function from the y-intercept.
From there, we move to energy levels and line spectra, exploring the internal structure of the atom. Why do heated gases emit light only at specific, characteristic colors, acting like a chemical fingerprint? You discover that electrons bound to an isolated atom can only possess specific, negative, quantized amounts of energy. We calculate the exact wavelengths of photons emitted or absorbed during electron transitions. Crucially, you interpret emission bright line spectra and absorption dark line spectra as direct, undeniable evidence for these discrete atomic energy levels.
Then, the universe flips the script with the concept of the de Broglie wavelength. If light waves can act like particles, can solid matter, like a moving electron, act like a wave? You calculate the de Broglie wavelength of moving particles and look at electron diffraction through graphite as experimental proof of wave-particle duality. We then culminate with the Heisenberg uncertainty principle, exploring the fundamental, inescapable limit to how precisely we can simultaneously measure conjugate quantities like position and momentum. Quantum physics is heavily examined in Paper 4, demanding both precise calculations with very small numbers and deep conceptual written explanations. You master photon energies, the photoelectric equations, atomic spectra, and matter waves. The mathematics is generally straightforward algebraic substitution, but the concepts completely change how you view reality. The A-star candidate separates themselves by mastering the written explanations. Let's get started.